Okay. So, very good morning to one and all. This is Professor Cyril Prasanna from MS Engineering College. Let us continue with the discussions that we had since last class. So, as I had mentioned earlier in my class, so I will be talking about communication systems. And last class, what we actually learnt was a very brief introduction to communication systems. So, I had mentioned about the importance of communication. I had also mentioned about why communication is required and what are the elements of communication, and also mentioned what are the three types of communication techniques, which are all classified under analog modulation and demodulation techniques, that is amplitude modulation, frequency modulation and phase modulation. So, what we do today is try to continue with the concepts of amplitude modulation. So, let us understand what is communication system is all about. So, as I mentioned in my earlier class, so we have an input data that has been captured by a sensor. Maybe the speech is captured by a microphone. So, the sensor converts the data from physical quantity to an electrical signal, and then it is given to a transmitter. So, the sensor and the transmitter, they are the blocks that are available on one side, that is the source side, and the transmitter basically takes the signal coming out from a sensor and then tries to do all the processing activity such that the signal is now ready for transmission, and the parameters of the signal are compatible as per the channel requirements. So, if at all a signal has to be launched onto a channel, we need to have a transducer there, wherein which converts electrical signal back to physical quantity. In our case, the channel basically accepts electromagnetic wave. So, to convert an electrical signal to an electromagnetic wave, we use an antenna. An antenna is basically a short device, which is a conductor which takes in alternating current and converts that alternating current to an electromagnetic wave, and that is what basically forms the transmitter section, or we call as a source. As the electromagnetic wave that is being generated from an antenna is traveling over the channel, at the receiver we again have an antenna which captures this electromagnetic signal and converts that electromagnetic signal to an electrical signal. So, now that is again a transducer there which is trying to convert electromagnetic signal to an electrical signal, and that signal is again taken to a receiver, and the receiver does all the reverse processes, to ensure that the information is extracted from the received data, and then the signal is given to an actuator which converts the electrical signal back to physical quantity. A simple example for an actuator is a speaker. So, these are the elements of a simple communication system. Now, we will try to understand, if at all you would like to transmit the data from a source to a destination, there is a process called modulation. So, as I mentioned in my earlier class, the process of modulation is translating a frequency from low to high, is what we call it as modulation. Okay. So, the process of converting or translating your incoming signal coming from a sensor to a frequency of higher range is what we call it as modulation. And at the receiver side, the high frequency signal that are received by the antenna is converted back to the low frequency signal or the information signal, and that is what we call it as demodulation. So, these are the two important concepts of communication system that are as per the syllabus of VTU, wherein we try to understand what is modulation and what is demodulation. So, let us now understand what is your modulation, particularly the analog modulation, that is amplitude modulation. So, as I mentioned in my previous class, a microphone captures an incoming signal which is physical quantity, and that physical quantity we know that we are talking at a frequency range of 20 Hz to 4 kHz. These frequencies are now captured by a microphone. The microphone takes this signal, converts into an electrical data, and then it is given to an amplifier so that the signal strength is actually improved, and that output of an amplifier, it is again in the same frequency range of 20 to 4 kHz, and we call this as baseband signal. Now, if at all you would like to transfer this baseband signal through a channel, we have a carrier signal there, that is we call it as high frequency carrier. Now, this high frequency carrier and this baseband signal are modulated, and then you get a modulated carrier. This modulated carrier is in the frequency range of 900 megahertz to 1800 megahertz in a typical application of mobile phones. Now, this modulated carrier will be now further amplified and given to an antenna for transmission. Now, the process of converting or process of translating your baseband signal to a modulated carrier with the help of a carrier signal is what we call it as modulation, right? Now, let us understand the components of modulation. The components of modulation, if you see, we have a carrier signal, we have a message signal, and then we try to program, we try to ensure that the carrier signal is able to carry the message data and it is now reaching the destination. Okay, this is what we discussed last class. Now, let us continue with the discussions what we are going to do today, right? Now, so if at all you try to understand why should we do modulation. Okay. So, the purpose of modulation is, as I mentioned, there are three important activities of performing modulation. The three important activities of modulation are like, one is length of the antenna. Okay, that is, if at all you take a baseband signal of for example 3 kilohertz range, we know that the length of the antenna should be lambda by 4, where lambda represents the wavelength of the signal. And we know that lambda is given by C by F. If at all you calculate the length of an antenna for transmitting a 3 kilohertz signal, the length of the antenna is around 25 kilometers. This is huge length. It is highly impossible for anybody to have such huge antennas to be carried along with your mobile phone to transmit a signal that we speak. If at all you translate this frequency from 3 kilohertz to 900 megahertz, okay, I have just done a simple calculations over there, and you find that this signal, once it is translated from 3 kilohertz to 900 megahertz, okay, as the frequency keeps increasing, the length of the antenna reduces. So, you need to have an antenna of 8 centimeters. Okay. So, that is typically possible, because it is practically possible, it is a very small in size. So, if at all you have an antenna of 8 centimeter, it is definitely possible to carry your mobile phones in your pockets, right. So, if at all you translate a frequency of 3 kilohertz to 900 megahertz, the length of the antenna that is required to transmit as well as for receiving the data is going to be reduced. That is the advantage of modulation. So, let us summarize. The length of antenna is reduced if the transmitting and receiving frequency is greater. So, this improves device portability. That is one of the significant advantages of performing modulation. Let us see what is the second important advantage of performing modulation. Now, we call it as a simple term like multiple channels can be used. What do you mean by multiple channels? Let us understand that we have a source. Okay. So, we have a source 1. So, this source 1, okay, if you take this source 1 may be user 1. Okay. So, I may be speaking through my mobile phone, and source 2 maybe my friend is talking from a mobile phone, and source 3 another friend is also talking from a mobile phone. All these mobile phones have microphones which captures the signal, and these signals, since all of us are able to speak, and we also know that the speech signal is in the range of 20 to 4 kilohertz. So, all the microphones will be able to capture data, and the frequency range would be 20 to 4 kilohertz. Now, this signal that is coming at 20 to 4 kilohertz data is amplified by an amplifier, and it is now given to an antenna for transmission. Once you transmit this data without modulation directly onto a channel, let us see what would happen. The signal coming from this antenna is going to be 20 to 4 kilohertz. The signal coming from this antenna is also going to be 20 to 4 kilohertz. The signal coming from this antenna is also going to be 20 to 4 kilohertz range. And as long as all of them are now available in a communication channel, okay, what happens is all these channels gets mixed up. So, suppose if these signals are now receiving or being received at a receiver antenna, now the receiver will be now completely confused. He may not know which signal is actually trying to receive, because all the frequencies are in the similar range. So if at all you understand this, it's a very nice way of understanding why we should go for modulation. So all these signals that are being transmitted without modulation are in the same frequency range of 20 to 4 kilohertz, and because of that the receiver will be now completely confused and it will not be able to recognize which signal is coming from which station, which source. So if at all you would like to segregate, if at all you would like to bifurcate, if at all you would like to understand, okay, this signal is from source 1, this signal is from source 2, and this signal is from source 3, let us see how we can actually take care of these activities. Yes. Yes. Okay. So what we do is, instead of transmitting the data directly from the microphone to an antenna, let us perform modulation here. So what is the modulation that we do here? So we try to, use a modulator here, modulator 1, and what we do is, this modulator will be assigned a carrier frequency of 900 megahertz. That means any signal that is coming from source 1 would be carried by a carrier which is operating at a frequency of 900 megahertz. Similarly, the signal that is coming from source 2, which is again going to be from 20 hertz to 4 kilohertz, is now being carried by a carrier signal of 1200 megahertz. So the frequency that we assign to the first channel is 900 megahertz, the frequency that we assign to the second channel is 1200 megahertz. Similarly, the frequency that we assign to the third channel is 1400 megahertz. So now what happens is, if the carrier frequencies like 900, 1200 and 1400 megahertz are assigned to each of the stations or the sources, now what happens, the incoming signal will be automatically translated to a frequency range of 900 megahertz plus or minus 4 kilohertz. Similarly, the second source will be now assigned a carrier frequency of 1200 megahertz plus or minus 4 kilohertz, and the third signal will be transmitted using a carrier of 1400 megahertz plus or minus 4 kilohertz. So what happens, there is a clear demarcation between channel 1, channel 2 and channel 3, because the frequency of channel is 900, the frequency of channel 2 is 1200, the frequency of channel 3 is 1400. So what happens, if all the three carriers are now made available onto a channel, and if they are all available onto a channel, all of them may be available on the channel, but the difference here is all of them are now available at 3 different frequencies. Now the antenna would receive this data. Once the antenna receives this data, it will be able to receive all the 3 signals. All the 3 signals are received here. Now what the receiver has to now do is, it is now left to the receiver to choose which source he is supposed to listen to. He can tune his receiver to 1200 megahertz. So automatically what happens, he will be able to receive all the signals coming from source 2. He can tune the receiver to 1400 megahertz. So he can receive all the signals coming from source 3. So the user now has a choice to choose from all the 3 sources, and that is possible only because of modulation. So this is the second advantage of modulation. Now let us go to the third advantage. Okay, so let us go to the third advantage of modulation. So what we do here learn is the concept of narrow banding. So it's a very interesting thing which I also appreciate why modulation plays a very important role. Okay, the concept of narrow banding basically refers to, let us assume that the audio signal that is going to be transmitted is has a frequency range of 50 hertz to 10 kilohertz. I'm just assuming that there is a signal that is available which is basically from 50 hertz to 10 kilohertz. Assume that there is a recording happening, there is a musician playing music, is able to sing, plus there are lots of instruments also being used to synchronize his voice. So what is happening is, basically there is a audio recording happening and the frequencies are from 50 hertz to 10 kilohertz. So low frequency is 50 hertz and high frequency is 10 kilohertz. In between we may have multiple other frequency components. Now suppose we calculate the length of the antenna required to transmit or to receive. The frequency ranges from 50 hertz to 10 kilohertz. Let us find out the ratio of the highest frequency to lowest frequency. So what we do is, we divide 10 kilohertz So we are trying to divide 10 kilohertz by 50 hertz to find out what would be the ratio between the highest frequency to the lowest frequency. It is found that it is going to be around 200 is the ratio. Now what do you mean by 200? That is the antenna size. If you consider the antenna size, which is having a length L is given by Cf by lambda, we should now have an antenna of variable sizes. You are able to see the picture here. Okay, now the lowest length, the lowest element that you find in an antenna, okay, this is able to receive 10 kilohertz signal, and the highest the largest the longest antenna that you find over here, the element on an antenna is now able to receive 50 hertz signal. So you need to have multiple elements on an antenna to receive all the signals from 50 hertz to 10 kilohertz. Now if at all you would have visualized some of the antennas maybe around 10 years back, we used to have very large antennas installed on our houses to receive the Bangalore DD channels. I don't know whether you have looked at those antennas. We had a huge antenna that was erected to only receive the signals from various stations, and these antennas were having this kind of elements available on them, and that is to ensure that you receive frequencies from both 50 hertz to 10 kilohertz. Let us understand now. The element that is available in an antenna, which is around 10 kilohertz, the element that is available, which is the longest element available, can receive 50 hertz signal, and the shortest element that is available over here can receive 10 kilohertz signal, because the ratio between the highest frequency to lowest frequency is going to be around 200. Okay, and this is the different elements that are required on an antenna for transmission and reception without modulation. If at all we try to now modulate, suppose if you take the audio spectrum that is from 50 hertz to 10 kilohertz, and if you modulate or translate that using 1 megahertz signal, so that means you are taking a data from 1 megahertz and you are translating by 50 hertz. Similarly, the highest frequency 10 kilohertz is also going to be translated by 1 megahertz. So if you try to now find out the ratio between the highest frequency to the lowest frequency after modulation, the size, the antenna ratio would be now 1.01. See, this is a very interesting fact. Okay, it's a 1.01. So if at all you perform modulation and then you translate the lowest frequency that is 50 hertz and highest frequency that is 10 kilohertz by a carrier signal of 1 megahertz, now the ratio between the largest frequency to the smallest frequency is 1.01. So now what happens, the number of elements or the length of the elements that are required in an antenna is now going to be 1.01. So from 200 you are reducing it to 1.01. So number of elements are required are going to be very less, and you require a very small antenna, and we call this concept as narrow banding. Okay, thus the process of modulation changes wide band signal to narrow band signal. It's a very, very interesting activity that we may have to understand and appreciate the process of modulation. Okay, let us now summarize. Okay, so now modulation is a process of translating modulating signal, okay, to control the amplitude or frequency or phase parameters of carrier signal termed as high frequency to achieve a reliable communication. That is what is modulation is. Now the advantages of modulation are, see, there are three important advantages of modulation. One is the length of the antenna is going to be reduced. That is the advantages of modulation. Then second advantage of modulation is, using modulation you can now have multiple channels which could be transmitted over a single channel, and that is the concept of multiple channels. And third important property is, okay, narrow banding. Okay, so because of modulation, the narrow banding concept also comes into picture. Apart from that, you also have multiplexing of signals. You also have errors in channels that is not going to corrupt your information because of the process of modulation. Okay, now these are the very important factors that you may have to understand, okay, and also reproduce when you try to write an exam, okay, on modulation techniques. Okay, yes, let us now go to the next important aspect. Okay, now if at all you would like to further learn more about modulation and also get the lecture notes and more discussion on this, you can visit the website or web link www.research.mscc.ac.in. we have an ebook available, you can download more information, or you can also visit the EduSat details, get information about these factors, right? Okay, now let us understand the first and foremost important thing, the analog or amplitude modulation, right? Now let us revisit the carrier signal. Okay, so the carrier signal, which is always a high frequency signal, is represented by a mathematical equation Vc of t, okay, which is called as the instantaneous amplitude of the carrier, is equal to Vc cos of omega ct plus phi c. That is, Vc is the amplitude of the carrier signal, omega c is the carrier frequency, which is given by 2 pi fc, and phi c is the phase information available in the carrier. So there are three important parameters that define a carrier signal. What are three important parameters now? The three important parameters are: one is the amplitude of the carrier denoted by Vc, second is omega c, the frequency, okay, and the third is phi c, which is the phase information. Now if at all you take a modulating signal, which is again we are considering here to be a single sinusoidal signal or cos signal, okay, that is Vm cos of omega mt. If you take this modulating signal, that is Vm cos of omega mt, this Vm cos of omega mt, which is called as the modulating signal, okay, this modulating signal can change the amplitude of your carrier. If at all the modulating signal changes the amplitude of the carrier, we call that as amplitude modulation. Similarly, if at all this Vm is able to change the frequency of the carrier, we term it as frequency modulation. If at all Vc is able to change the phase of the carrier, we call that as phase modulation. So these are the three basic modulation techniques that are available: amplitude modulation, frequency modulation, and phase modulation. Now let us understand the first important aspect called as amplitude modulation, right? Okay, let us now get into the details of amplitude modulation, right? Okay, yes, let us now understand the concepts of amplitude modulation with mathematical equations. Now if at all you would like to get full marks for all the answers what you write in your exams, okay, the important concept that you need to adopt is, if you write an answer, ensure that you first produce a definition, then you try to put a block diagram or try to put a graph. Third important thing is use mathematical equations and then use some examples. So these are the four components that are going to be associated with writing an answer to get full marks. One is clear brief description to the answer, you try to write a block diagram or a graph, mathematical equation, and an example. Four components would definitely fetch you full marks. Now let us understand the concepts of amplitude modulation with the process of mathematical activities. Now the process of modulation is always carried out with the mathematical operation called multiplication. So let us understand, any kind of communication activity is dependent upon a process called multiplication. So if at all you multiply your modulating signal m of t with carrier signal Vc of t, we term it as modulation. Let us understand what is amplitude modulation is. Okay, now we know that m of t is given by cos of omega mt and Vc of t is given by cos of omega ct. So where omega m is your modulating frequency and omega c is the carrier frequency. So what we do is we multiply the modulating signal with the carrier signal. So if you see the mathematical equation, that's a very interesting thing. If you multiply omega m of t with the carrier frequency omega c of t, okay, we find that there are two terms there, that is cos a and cos b. We know that cos a cos b is going to be what? Half of cos of a plus b and cos of a minus b. That means you are able to now find out that there are two terms that are going to be generated after multiplication process. The two terms are omega c plus omega m, and then omega c minus omega m. So that means because of the multiplication that is being done, okay, you are trying to multiply m of t with Vc of t, you are now able to generate two signals, omega c plus omega m and omega c minus omega m. Now if you try to take this omega c plus omega and omega c minus omega m, we know that omega m is low frequency, omega c is high frequency. Suppose if you take omega c is going to be 100 kilohertz or omega m is going to be 1 kilohertz, after multiplication process you are able to now get, okay, 101 frequency, 101 kilohertz as one frequency and 99 kilohertz the other frequency. So by assuming that omega c is 100 kilohertz and omega m is supposed to be 1 kilohertz, okay, 1 kilohertz and this is 100 kilohertz. If you take this, so what happens now? By performing multiplication, one frequency that we are able to get after modulation is the higher frequency, that is 101 kilohertz, the lower frequency is 99 kilohertz. See how nicely the modulation is able to give us, or the multiplication is now able to give us two frequency components, 101 and 99 kilohertz. Now if you transmit both these frequencies over the communication channel, we are now receiving both these signals at the communication receiver. When both the signals are being received at the receiver, okay, to get back omega mt from the received signal, what we do is further at the receiver we take the received signal, that is m of t into Vc of t, and further multiply it with another Vc of t. See how interesting the things, mathematical equation helps us in understanding what is communication is. Let me now repeat it. At the receiver is what is happening now, the m of t signal, the m of t signal that you are able to transmit, m of t into Vc of t, which is the signal that has been modulated and transmitted, is further multiplied by another carrier, that is Vc of t. Now assuming that the signal that is available at the carrier Vc of t is equivalent to the signal available at the transmitter, that is Vc of t, you can substituting this, you find that the Vs of t will be now equal to cos of omega mt, cos of omega ct, again cos of omega ct, which is now equal to cos of omega mt into 1 by 2, 1 plus cos of 2 omega ct. Again it's a trigonometric function that we use over there. So you find that it is cos of omega ct into cos of omega ct is now going to be cos square omega ct. Cos square omega ct is now going to be what? 1 plus cos of 2 omega ct by 2. So that's what we have done here. Now if you further expand this, it is now going to be cos of omega mt, cos of omega mt into cos of 2 omega ct. We are neglected the 1 by 2 ratio there, right? So it is cos of omega mt plus cos of omega mt into cos of 2 omega ct. So if you find the mathematical operation that is being performed at the receiver, because of multiplying the incoming signal by cos of omega ct, which is the carrier signal that is available at the receiver, we are now able to get omega mt as one of the signal over there, and then we are able to get another frequency which is now going to be translated by twice. Now if at all you see this omega mt plus omega mt into cos of omega 2 ct, we can filter this off using a low pass filter, or no, we can remove this using a filter and only retain this, so we get back omega mt. So by performing a process of multiplication at the transmitter with Vc of t, again by performing a multiplication of the received signal by Vc of t, we are able to transmit, or we are able to translate a low frequency signal m of t to high frequency signal, and again get back cos of omega mt or m of t at the receiver, and that is the beauty of modulation. So let me summarize. M of t is multiplied by a carrier Vc of t and it is transmitted, and to further get back m of t at the receiver, we again multiply it with Vc of t. So now what you find now is after multiplication process we get back cos of omega mt. So we are able to transmit as well as receive data by just performing a process of modulation, and that is what is your carrier that is required, Vc of t, right? Now let us understand what are the limitations of this multiplication process. The limitations of this multiplication process are, again, at the transmitter we are using a carrier Vc of t, okay, and it is now being used for multiplication, and it is cos of omega ct, right, represented by cos of omega ct. Now once this is being transmitted at the receiver, we are assuming that the received signal is again going to be multiplied by a carrier signal cos of omega ct. Now the assumption that we do here is the signal that is available at the receiver, the cos of omega ct signal, okay, available at the receiver, and the cos of omega ct signal available at the transmitter, both of them are same or identical in terms of frequency, in terms of phase. So this is one of the assumptions that is being made. Because of this, what we now achieve is, by assuming that the frequency and phase of transmitting carrier, the frequency and phase of the carrier used at the receiver, both of them are identical, we are able to get back cos of omega mt, that is the modulating signal at the receiver. If at all the signal that is available at the receiver, instead of omega c, if it is omega c1, okay, instead of 100 kilohertz, if it is deviated by 101 kilohertz, or if there is a small amount of phase difference between the transmitted carrier and the received carrier, it is not possible to get the signal omega mt because of multiplication process. Why? Because if at all there is any small amount of deviation, okay, in terms of frequency and phase of the signal that is used at the receiver, then it is not possible to get back omega mt, and that is one of the major limitations of this process. Now, the limitation here is, okay, let me summarize, the carrier signal that is used at the transmitter and the carrier signal used at the receiver, to get back to modulate as well as to demodulate, the frequency and phase of the carrier signal should be identical. But in practical considerations, this may not be the same, because your transmitter will be at one station, receiver will be at the other station. You have to always maintain a constant synchronization aspect between the transmitter as well as at the receiver. Now, if this is the scenario, it will be very difficult for us to get back the modulating signal. So, how do you perform amplitude modulation? So, now let us understand the process of amplitude modulation. How interestingly, how effectively, yes, people have come out with a very interesting equation called the modulating equation. Now, this is a very interesting factor here. So, let us take the carrier signal once again. It is given by, okay, Vc of t is equal to Vc into cos of omega ct is the carrier. Okay, we are all aware of it. Now, this carrier signal, okay, whatever we have, before it could be multiplied by the modulating signal, what we actually do is, we take the modulating signal m of t, okay, and then add a DC component called VDC. See, let us see how what is going to happen now. A modulating signal m of t is now going to be added with a DC signal called VDC. Now, the output of this addition process is VDC plus m of t. See how now what is the advantage? Let us understand what is the advantage of this now. VDC is a DC signal, okay, and m of t is a modulating signal now. Now, when we try to add the DC signal with the modulating signal, we get an output called VDC plus m of t. Now, this VDC plus m of t is now going to be multiplied by the carrier signal cos of omega ct, and that output whatever we get is now called as the amplitude modulated data. So, the expression for amplitude modulation is given by Vs of t is equal to VDC plus m of t cos of omega ct. Now, let me expand this. Once you expand this, it is now equal to Vs of t is equal to VDC into cos of omega ct plus m of t cos of omega ct. So, there are two terms in your amplitude modulation signal. What are the two terms now? The two terms are cos of omega ct, the first term, and the second term is m of t cos of omega ct. This is the second term that we come across in the amplitude modulated signal. Now, what we saw earlier was only this data, m of t into cos of omega ct is the data that we understood as modulation, and we could transmit the data. But now, along with that m of t cos of omega ct, what is that we are trying to do? We are also giving, okay, cos of omega ct, that is the carrier, the unmodulated carrier, along with the modulated carrier, both of them are now made to travel, or both of them are now transmitted over the channel. So, now let us understand the advantage of this. The advantage of transmitting both the carrier as well as the modulated carrier in analog modulation is, once you receive the signal, once you start receiving the signal at the receiver, okay, you don't have to generate carrier signal at the receiver. Instead, what we can do, we can use the same carrier signal at the receiver and start multiplying it with this. And once you receive the same signal that is available from the received data, now what happens, since the carrier signal is now not generated at the transmitter, at the receiver, we are using the carrier signal that was transmitted from the transmitter. So what happens, the carrier frequency that is used at the receiver and the carrier frequency that is carrying the information, both will be identical and there will be no any deviation in terms of frequency as well as phase, and that is the advantage of having this amplitude modulation. So it's a very interesting thing that all of us have to really understand, why we are supposed to have VDC into cos of omega Ct plus m of t cos of omega Ct. So let me summarize. The advantage of this is, see, cos of omega Ct into m of t produces what? Translates low frequency to high frequency. That's done. Now, since we have to get back m of t at the receiver, and to get back m of t, we have to further multiply this with cos of omega Ct. And if cos of omega Ct that is used at the receiver, if it is not identical to the cos of omega Ct, that is the carrier signal at the transmitter, it is impossible to get m of t. To avoid that kind of activities, what we now do is, along with m of t cos of omega Ct, we also transmit the carrier signal, and that is how we have cos of omega Ct VDC term there. Now what we do is, at the receiver, okay, once we receive this as well as this, we use this carrier signal to extract m of t from the modulated carrier, and that is what is the mathematical expression for amplitude modulation. So if at all they ask you what is amplitude modulation, the expression that we are supposed to now write for amplitude modulation is this. Okay, it is Vs of t VDC cos of omega Ct plus m of t cos of omega Ct. The first term is the carrier term, the second term is the modulated carrier, and that is the mathematical expression for amplitude modulation. What is the block diagram? The block diagram is, VDC is the DC signal. We are trying to add the DC signal with m of t, you get VDC plus m of t. The DC shifted modulating signal is now multiplied by the carrier to get Vs of t, that is the modulated carrier. So this is the block diagram. Okay, this is the block diagram that we come across, and this is the mathematical equation to illustrate what is amplitude modulation, right? Okay, good. Yes, let us now go to the next important aspect. Okay, let us further understand what are the basic components of amplitude modulation. Okay, we know that the mathematical expression for Vs of t, that is amplitude modulation, is VDC cos of omega Ct plus Vm cos of omega mt into cos of omega Ct. Using the trigonometric formula cos A into cos B, the second term that you come across over here, the second term that we come across over there, okay, the second term is expanded to this equation. Now we find that there are three important terms in the amplitude modulation signal. Three important terms are, the first term is this cos of omega Ct, that is carrier signal. Second term is omega C plus omega m, that is obtained from the second term available here. The third term is omega C plus omega C minus omega m, that is the third important term. So there are three important components in amplitude modulation. The three important components are omega Ct, the first term, omega C plus omega m, the second term, omega C minus omega m, the third term. Let us also understand there are three important amplitudes. The three important amplitudes are, the carrier signal is having an amplitude of VDC. The modulated carrier has an amplitude of Vm by 2 and Vm by 2. Okay, the modulating signal Vm has been now reduced by Vm by 2, and VDC is now the amplitude of the carrier. Now let us understand what are the three components of amplitude modulation signal. The three components of amplitude modulation signal are, what is first component now? In terms of amplitude, we have VDC of the carrier. Then the signal, that is omega c plus omega m, we call it as upper sideband, which is having an amplitude of Vm by 2 and a frequency of Fc plus Fm. The third component, called as lower sideband, has an amplitude of Vm by 2, okay, and a lower frequency, that is omega c minus omega m, or there is a mistake here, it is omega Fc minus Fm. These are the three components of amplitude modulated signal. Okay, let me summarize. After performing modulation of incoming signal by a carrier, there are three components that we come across in an amplitude modulation signal. The three components are carrier, frequency, and your amplitude, upper sideband and lower sideband. These are three important components that comes across after performing modulation, right? Okay, good. Let us go to the next slide. Yes. Let us understand the AM signal in detail further. So, the three components that we obtained after modulation is VDC cos of omega ct, the first component over there. Yes. Yeah, the first component that we got was VDC cos of omega ct is the carrier signal. Then second component is Vm by 2 cos of omega c plus omega m. Third component is Vm by 2 cos of omega c minus omega m. Now, let us understand the frequency spectrum of this signal. So, if you see Vm, that is your Vm m of t, which is having a frequency of omega m, has a spectrum like this. Okay. Once it is DC shifted, okay, there is a DC bias now. This is the amount of DC bias what you come across. Further, the carrier signal that you come across here has a higher frequency, there is a single spectrum, and this is the carrier signal. Now, what you do is when you multiply your m of t VDC, that is VDC plus m of t into the carrier, this is the representation of AM signal, that is amplitude modulated signal. You find that this carrier signal, this modulating signal is now available over here, but it is shifted by a DC bias equal to VDC. Since there are two bands, higher frequency as well as lower frequency, one band is this and the other band is at the bottom, okay, but again shifted by VDC. Okay, this is again shifted by VDC. So, to represent an AM signal in terms of time domain, the upper sideband of AM is here, lower sideband is here, which is m of t, and in between you find that there is a DC carrier available in between. VDC is the carrier now. So, with respect to this VDC, the carrier signal is been modulated and you are able to get upper sideband and you are able to get lower sideband, right? Okay. So, in your exam you may have to represent this expression, you might this block diagram, you might represent this mathematical equation, then you have to represent this time domain process. This is the time domain representation of AM signal, mathematical equation for AM signal, and the block diagram for AM signal. All the three you have to present in your exams, right? Okay. Yes. Let us understand this AM signal further in detail. Okay. Now, we know that the modulated carrier, because of amplitude modulation, is given by this expression. This expression now what we come across. Yeah. The expression that we come across for your modulation is this. We can also rewrite this expression in terms of this. By removing VDC outside, it is now VDC into 1 plus Vm by VDC cos of omega mt into cos of omega ct. the term Vm by VDC, okay, we call it as modulation depth. So let us understand what is this modulation depth is. Okay, here if you try to understand, Vm is the amplitude of the modulator message, VDC is the DC shift, right? Now the modulation depth is basically Vm by VDC. So if at all you have a very small amount of modulating signal strength, you are shifting it by a factor of VDC, and the modulation depth is now equal to Vm by VDC. Let us understand what is the importance or what is the significance of this modulation depth Vm by VDC. Okay, yes. Okay. Now this AM signal, which is graphically or using a time domain process, is represented by this expression. So you have Vm here, this is the modulating signal over there. Okay, so we have Vm on one side, okay, then VDC is the carrier. Now you find that after modulation, okay, the lowest amplitude of the AM signal, okay, the peak to peak is given by 2 times of E minimum, and the maximum output or the maximum peak is going to be given by 2 times of E max. Now what we do is we can also express the modulation depth, okay, that is M, in terms of 2 E max minus E minimum, that is Vm, and 2 E max plus 2 E minimum in terms of VDC. So if you see Vm will be basically equal to 2 E max minus 2 times of Em, that is your Vm, okay, plus VDC, or that is divided by VDC, which is going to be 2 E max plus 2 times of Em, and that is going to be your VDC. So this VDC is now represented by E max plus 2 times of Em, and Vm is represented by 2 E max minus 2 E minimum. Okay, so that is another way of expressing your modulation depth. Okay, yes. Okay. Here what we understand here is what are the modulation depth conditions. So we know that modulation depth is Vm by VDC. Okay. Now if you assume that Vm by VDC is less than 1, the first condition. So the first condition is Vm by VDC is less than 1, or Vm by VDC, that is M is greater than 1. So if at all M should be greater than 1, okay, so your Vm is going to be larger, that is Vm is going to be greater than VDC. If the Vm frequency is going to be more than VDC, sorry, we have sorry for this, let us go back. Yes. Yeah, the first condition. In the first condition, what we do here is M is equal to Vm by VDC, that is the modulation depth. If Vm is less than VDC, means the DC shift that you are going to provide onto modulating signal is going to be larger than the maximum amplitude of modulating signal, that is if VDC is greater than Vm, okay, or M is less than 1, this is what we get here. So we find that you have 3 components, VDC is one component, okay, then Vm by 2 higher frequency, and Vm by 2 it is the lower side band. Okay. Now if Vm is equal to VDC and if modulation depth M is equal to 1, you have these waveforms. So if you say try to understand here, okay, M is equal to modulation depth, and for a condition when M is equal to 1, the carrier amplitude is now equal to the maximum Vm amplitude, that is the modulating signal amplitude. So what happens, you are able to come across this. Suppose if it is M less than 1, we have this signal. Okay. Now what is the difference between this and this? The difference between the first and the second is, in the first one, okay, the amplitude of the carrier is larger. Because the amplitude of the carrier is larger, we are able to get this signal over here, and your M is less than 1. If at all, if the Vm is equal to VDC, okay, that is the amplitude of the carrier is equal to the modulating signal, you come across this waveform. So what happens, the signal strength is going to be reduced, okay, because there is no any DC shift that is going to occur, and the signal strength is now going to be reduced, and then you find that, okay, you come across this information, right. Now if you try to further change this modulation depth, okay, from m equal to 1 to m greater than 1, let us see what is going to happen now, okay. Yes, if you make m greater than 1, what is going to happen is you come across a concept called phase reversal. It is a very interesting aspect in amplitude modulation. Phase reversal occurs when you try to make m greater than 1, that is your DC shift on the carrier, okay, that is the DC shift on the carrier is now going to have a strength less than the amplitude modulation signal. So if at all you see here, if VDC is less than Vm, there is a phase reversal that is going to occur, because m is now going to be greater than 1. Why? What is the significance of this phase reversal now? The significance of phase reversal is, see, if you take a modulating signal here, this is your upper frequency and this is the lower frequency. Now because of the modulating depth going to be greater than 1, what would happen is, the signal that is here, the signal that is going to be available here, because of the modulation depth going to be greater than 1, this signal will come out like this. So it is now going to the other side, okay, that is the negative side, and this signal that was available here is now going to be the positive side. That means the phase is now going to completely change. Because the phase is now going to change, the lower sideband is going to the upper sideband and upper sideband is coming to lower sideband, it now becomes very, very difficult for us to perform demodulation of the message from the received carrier. That is why you should not, you should avoid modulation depth to be greater than 1, because signal or information is going to be completely lost. So the process of phase reversal is, okay, if at all we increase or if at all we reduce the strength of the carrier signal, that is VDC, less than modulating signal Vm, what happens, a phase reversal occurs and information is completely going to get lost. So we need to ensure that always the modulating depth is going to be either equal to 1 or it is going to be less than 1 in amplitude modulation. Finally, let us understand what is the power in an amplitude signal. Okay, what is the power? That is, if at all you want to transmit an amplitude signal, we have to provide some amount of power. What is the amount of power that is going to be consumed by amplitude modulation data? So the power that is going to be consumed can be computed by the simple expression. Okay, the normalized average power is given by Vrms square. Okay, if at all you try to square the voltage, you get power. It is V peak by root 2 whole square. Using this formula, okay, using this simple formula, we can now find out what would be the total power of the carrier. The total power of the carrier Pt is now given by the carrier power, the first term, the power of the upper sideband, the power of the lower sideband, all the three you can compute it, because we know amplitude of power carrier signal VDC, lower sideband, upper sideband and lower sideband. By using this formula, we can now find out what will be the power of all the three components. It is going to be VDC square by 2 and m square VDC square by 8 and m square VDC square by 8. By adding all of these three, by computing or by adding all these three things together, yes, by adding all the three together, the total power of amplitude modulation is given by Pt is equal to, it is given by Pt is equal to Pc into 1 plus m square by 2. So let me stop here. So the total power consumed by amplitude modulation is Pt is equal to Pc into 1 plus m square by 2. Let me summarize what is Pc. PC is the power of the carrier given by the formula VDC square by 2, where VDC is the DC shift, and M is now called as the modulation depth, which is equal to Vm by VDC. So if you know modulation depth and if you know VDC, it is possible to compute the total power dissipated by amplitude modulation signal, which is PT is equal to PC into 1 plus M square by 2. Okay. So let me now summarize. So amplitude modulating signal consists of a carrier signal and two sidebands, and there is a parameter called modulation depth, which is given by Vm by VDC, and we need to ensure that Vm by VDC, that is M, modulation depth, is always going to be equal to 1 or it is going to be less than 1. If it is going to be greater than 1, we lose information. Then the AM signal power is given by PT is equal to PC into 1 plus M square by 2. So if at all you remember these three concepts, we have understood what is amplitude modulation. So let me stop here, and now there is an exercise. Discuss in detail the components of amplitude modulation signal and derive the total power of AM signal. So this is what a simple exercise that you can take up, and let us discuss this from next class onwards. Thank you.